Homomorphic encryption, it's one of those concepts that sounds like it's straight out of science fiction, right? The ability to actually compute on data while it's still completely encrypted. I mean, for data privacy, that's pretty much the holy grail. But like with any really powerful technology, there's always more to the story. So, okay, let's dive in.
And that right there, that's the fundamental tension we're going to explore. From an engineering perspective, this isn't just some clever algorithm in a paper. It's a tool. And just like any tool in your toolbox, it has its capabilities, sure, but it also has very real costs and limitations. Understanding that balance, well, that's the key to using it effectively.
That's the question, isn't it? It's the one every engineer has to answer before they even think about writing a single line of code. And we're not talking about money here. We're talking about performance, about complexity, and some really hard computational boundaries. We're going to break down exactly what that price is and what you really get in return.
All right, so before we get into all the limits and the gotchas, let's just establish what homomorphic encryption, or HE, actually brings to the table. At its core, it's all built on a surprisingly simple set of operations that unlock all its potential.
That's it, addition and multiplication. Seriously. Now, I know that might not sound like much, but just think about it for a second. Nearly any algorithm you can dream up, from simple stats to a complex machine learning model, can ultimately be broken down into a sequence of just these two things. This is the foundation. Everything else is built right on top of this.
Now, what's so cool about this is the security model it gives us. As a user, you encrypt your sensitive data on your own device. Then, you send that encrypted blob of data up to a powerful cloud server. And here's the magic. The server does all the work, all the additions and multiplications directly on that encrypted data, without ever having the key to see what's inside. Then, it sends the encrypted result back to you, and only you can decrypt it. The raw data is never exposed. That is the promise.
And this brings us right to the core of our discussion. We have this incredible security promise, which is fantastic, but now we have to face the practical realities of actually implementing it. This is where the trade-offs become absolutely critical. This slide really lays out the fundamental compromise. On one hand, you've got your standard, everyday plaintext computation. It's incredibly fast, it's flexible, you can run pretty much any code you want. On the other hand, you have encrypted computation. It gives you security, but it comes at a significant cost to both your speed and your flexibility. So let's break down what slower really means here.
Yeah, calling it slower is maybe the biggest understatement you can make. We are not talking about a 10% or 20% slowdown. We're talking about operations that can be thousands or in some cases even millions of times slower than their plaintext equivalents. Why? Well, it's because the encrypted data is just so much larger and the math involved is vastly more complex. This performance hit is the first and most important price you pay.
Now for the second price, a hard limit on complexity. So you can't just run an infinite number of calculations. Every HE scheme has this concept baked in called circuit depth. The best way to think of it is like a budget. You've got a certain number of sequential operations you can perform before the encrypted data basically just degrades into garbage.
And let me be really clear, this isn't a suggestion, it's a fundamental boundary. This limit forces engineers to completely rethink how they design algorithms. You have to create programs that are not only correct, but also shallow enough to fit within that allowed depth. It's a completely new kind of constraint you have to design for. So what causes the step limit? It's a phenomenon called noise. Think of it like this. It's like making a photocopy of a photocopy. The first copy looks pretty good, but when you copy that copy, a little bit of grain and imperfection gets added. If you do this enough times, the final image is just an unreadable, noisy mess. It's the same idea in HE. Every single computation adds a small amount of mathematical noise. And once that noise builds up and reaches a critical threshold, you can no longer decrypt the result correctly. The data is effectively lost.
Now this all might sound a little discouraging, I get it. But it's not a dead end, not at all. The field of cryptography has developed some really clever strategies to work within these constraints. It's all about being smart with your computational budget. And one of the most powerful strategies involves a different kind of trade-off. And this is a brilliant insight, especially for fields like machine learning or statistical analysis, where you don't always need a perfectly precise answer. Approximate HE schemes lean right into this reality. By accepting a tiny, controlled amount of error in the final result, they let you perform much deeper and much faster computations. It's a strategic trade. You give up a tiny bit of precision for a massive gain in capability. So after hearing about all these limitations, the slowness, the noise, the depth limits, it's pretty easy to feel like the technology just isn't ready yet. But from an engineering perspective, that's really the wrong way to look at it. These aren't failures. They're the rules of the game.
And this is the exact mindset of a practitioner. Knowing what the boundaries are is actually liberating. It transforms the problem from, can we do anything at all, to, okay, what amazing things can we build within these specific rules? It defines the puzzle for us, and now we can actually start solving it.
And that's really the question I want to leave you with. When you accept the trade-offs, when you work with the system instead of against it, what becomes possible? Secure analysis of medical records across hospitals without ever revealing patient data? Private financial audits? How about machine learning models that train on sensitive user information without ever actually seeing it? The price of this power is steep, there's no question. But for the right problems, it is absolutely a price worth paying.